Quantum tunneling is one of the weirdest things in the universe. If you throw a ball at a wall, usually it's not going to go through, unless you're Randy Johnson, I guess. And that's because there's a repulsive force that pushes back on the ball when it gets too close. This force comes from the electrons in the wall pushing on the electrons in the ball. If the ball isn't going fast enough, the repulsive force will slow it down before it can make it through. So there's a sense in which the wall functions as an energy barrier. The stronger the wall, the more energy the ball needs to break through, at least if the ball isn't quantum. See, a quantum ball isn't like an ordinary ball. Rather than having a defined position, a quantum ball exists in a sort of smeared out region. Now, if you were to try to figure out where the ball is, you'd find that the ball has a probability of being anywhere within its smeared out region, with the density of the smear telling you about the probability of finding the ball at a certain location. Now, before I continue, I need to give you one more technical detail. The density of that probability smear needs to be continuous, in the sense that the density at one location is very close to the density at nearby locations. This is essentially because of conservation of probability. If not, we would find that the probability of finding the ball at a particular place wouldn't be reproducible in the lab. Alright, back to tunneling. If left to its own devices, the smeared region will spread out all on its own, but the environment also affects how the smear spreads. And if there's an energy barrier, like a wall that requires more energy to overcome than the quantum ball has, well, you'd think you'd be stuck. But remember, the smear can't be discontinuous, which means that some of the probability smear has to leak through the barrier, otherwise the density would drop to zero suddenly, and that's not allowed. So the smear gets less and less dense in an exponential way as it continues to spread out inside the potential barrier, but eventually it'll spread out to the other side where it'll just do its normal spreading thing. So let's take stock of what I just said. In the presence of a barrier that classically could not be overcome, the probability smear sort of leaks through the barrier with decreasing but non-zero probability. And that means that there's a chance you'll find it on the other side of the wall. That's quantum tunneling, that the ball can pass through the barrier even if it didn't have enough energy to do so.